Yes, let's go to the fun. If you guys don't know, we ended here with some power series expansions, right? This came from the Maclaurin series. But to give you guys another example, to start to talk about some questions that have been brought up for me, let me give you guys an example of another power series. I think we looked at this yesterday. Let me see. Let me find it. All right, well, I thought I have it here. Okay, so even if we didn't, let's go back to the sheet. Yeah, there it is. Okay, I think we did do it, but okay. The natural log of 1 minus x is minus sum 1 to infinity. X to the n over n, and then you say, what's the interval of convergence? Let's take a look at this with a little bit detail, okay? We want to look at some of these details here for you guys. This is the power series expansion for this. So your book talks about, I've said, this is your interval of convergence because it is. I believe this came from the integration. This came from integrating. If you guys recall, we integrated the power series expansion for this, I believe. And that came from the integral x to the n 1 over infinity, or 0 to infinity dx, if you guys remember, something like that. And so the interval of convergence, this is that power series, comes from the fact that this was geometric, meaning the absolute value of r, which was the absolute value of x, has to be less than 1. So I kind of want to remind people a little bit of that detail, right? And so to kind of remark and recall that whether you differentiate a series, a power series, or whether you integrate it, you preserve the interval of convergence, which is what we're saying really here. So I'm just going to say here, recall where it came from. Now, what else we want to remark? But your book, you go, I get a little confused because the book says I got this x minus a less than r. What in the world does that even mean? Right? And what that really means is, by definition, that means negative r is less than x minus a, which is less than positive r. Since your interval of convergence right in here is what we have, I just have to remark that this is the same as x minus 0 less than 1. Okay? And so the a value is 0. So this is centered around 0 is what we're saying. And where the radius of convergence now, if I change the color, this is your radius of convergence, is 1. So this is the center, really, of that interval of convergence. So if you look at that detail, and then we say the radius of convergence, r, is 1. So that's what the book starts to say. Okay, the center of the interval is at A, and that radius is 1. Okay. Now, even from those other courses that you guys are taking, you get this relationship too, that a minus r is less than x, which is less than a plus r, I guess. Okay, we're running out of space. So just kind of tie up some loose ends. Gosh, I hate when it doesn't function. So this is kind of the equivalent. So your book kind of describes it that way. I've just described it just in terms of the interval, like this personally. But it's not like what they're saying is wrong. They're saying that's completely the same. So that's kind of an example here. Now, if they said to you, can you, what's the power series expansion now? Let's change this function on you guys, right? Like if they say, okay, we want the power series expansion for the natural log of 5 minus x. And find the interval of convergence. So power series expansion. And the interval of convergence. All right. So what you're going to use is what you have already. You go, how am I going to use this? Here's what you guys can do. I look at it this way. Since we proved that yesterday, and let's remove, this. Okay. So the question is going to be, well, how do I even use this? I think I did it. I'm sorry, I made a mistake. That's 5 minus x. I apologize. Okay? That's what they want, the power series expansion for this. So you say, well, how do I use that knowing the expansion we have? Well, understand that the natural log of 5 minus x is the same as the natural log of what? Okay, we need a 1, don't we? 1 plus 4 minus x. Is that true? So far, so good? That's the same as the natural log of 1. I need a minus here. So if I said to you, go back up here and factor out a negative. You go, what do you mean? Well, isn't that going to be a negative 4 plus x? Factor out a negative 1? Okay, isn't that negative times a negative positive? Right? You guys with me on that? And then negative times. So if you did this, we factored out a negative here. Then we get 4 minus x, I guess. And then you say, well, isn't this 1 minus, just change the terms, x minus 4 here. Okay, switch your terms. So this portion here is in green. Is in green. Is in green. Is in green. And there it is. You go, whoa. So that means the power series expansion is negative 1 to infinity. What's in green? The x minus 4 is in green here. We're going to use that portion. So x minus 4 to the nth power. Oh, Ren. Now that's your power series expansion. This is what they're looking for. Here it is. Now, I also have to say this. There's the power series expansion, but what is the interval of convergence? Now you're going to use this. Absolute value is less than 1. Now, but what is in there? That green portion here. So this is going to be absolute value x minus 4 is less than 1. And this is when you'll have what? Convergence here. So the book at this point will say, okay, that's good enough. There you go. You're done. There's your interval of convergence. You go, well, why does the book say that? Because they have you write it in this format, right? Where the center, this is centered at 4. With the radius of convergence, I forget what color, is 1. So, you know, that's kind of what they want you to see. The radius here, convergence is 1, and this is centered at A. But you might say, but Mr. Judge, what you've been doing is a little different. You've been saying, you've been using I guess, I don't know, intermediate algebra or pre-calculus, right? And so this is the same thing. Okay, so the intervals I've been giving you guys have been like something like this. So you say, oh, do you need to check the endpoints? No, you don't have to check these endpoints because it comes from that geometric series. This original, you know, power series came from geometric. So this is kind of, it's the same thing with the interval. And you say, but is this around 4? No, this is around, yeah, it's around 4. This is the center here, A is 4, right? The center of that interval. I've been calling that I. So just to kind of clear up for some people, like, what do they mean with this notation in the book? How is that different from what you're writing? Why are they asking for the center and the radius? I mean, it's kind of, it is interesting, but this is the interval, you know. And so you might even say to me, boy, the natural log, you know, the one thing that I love to show students is that if you approximate this function by the first few terms, right? And you go, well, how do I do that, right? What do we mean? I got to go back and forth. So what happens when it's 0? We got that negative sign, okay? I'll put the negative sign here. And if n is, well, you can't, oh no, it has to be 1, sorry. Can't be 1. So it'll be x minus 4 over 1, okay? So you have x minus 4 to the 1 over 1 minus x minus 4 over 2 over what? 2, is that true? Yes, now 3 minus x minus 4 cubed over 3. So that is going to be minus x minus 4 minus 1/2 x minus 4 squared minus 1 cubed x minus 4 cubed. And this is approximate. So you guys know what's coming. Natural log, so you guys can see that center idea. Where's your natural log? Darn it. Where's y? Okay. So, I mean, here's this curve they're talking about, natural log of 5 minus x. Now you might say, well, what's going on around that number 4? Isn't that the center of your, interval of convergence, right? Well, now let's look at these other things, right? Y equals negative, in parentheses, x minus 4. Come out, minus 1/2, right? And then you put what in parentheses again? X minus 4, come out of there, raise that to the what? Second power, minus, I think it was 1/3, right? 1 divided by 3. Put that in parentheses, x minus 4 raised to now 1, 2, 3. Okay? And let's change that color. We can change it to red. So what's the story in that particular interval from 3 to 5? Maybe you guys can see it better this way. Right? What's going on between 3 and 5? The curve is approximately the same. But it's very much the same around 4. Is that right? They're closer to the center. Around 4. So this is a good approximation. You're trying to approximate the curve with these. Now, could you get a better approximation if I add additional terms? Yeah. Minus 1 divided by 4, come out of there, parentheses, x minus 4 raised to what power? Isn't that 4? Don't you get an even better approximation in that interval from negative 3 to 5? You go, I can't even see that. Yeah, don't you get an even better approximation from negative 3 to 5? So the more terms you add here, minus 1 divided by 5, x minus what? 5 now, to the 5th power, between negative 3 and 5, the better you should get. Oh, did I screw up? Oh, I put a, there it is. Oh. There we go. I apologize. So take a look at the interval from negative 3 to 5. If you can see that, it's actually an even better approximation. So the more terms you include, the better the approximation of that curve. Centered around what? That value 4. Okay? Just want to kind of throw that out there because this idea of where this is centered is now the basis of Taylor and Maclaurin series expansions. Right? You guys know what I'm saying? You go, well, what's the difference between Maclaurin series and Taylor? The center. The center. Okay? So Maclaurin series expansion, we gave you guys that yesterday, right? What is that function expansion going to be? What is this? the sum, nth derivative evaluated around 0 over n factorial x to the n. And that goes from 0 to infinity. This is your Maclaurin series because the center A equals 0. That's the center of the expansion. Taylor series changes the center. This is what we seen yesterday. That's going to be from 0 to infinity, f to the n evaluated at a, n factorial x minus a to the n, because now the center is at a. Here, a is 0. And that is the difference between the two formulas for expansion, but they're based on derivatives. And so you might say, well, what's the deal? Can you have a different center? Yeah, you've seen one right now. That's a different center. This was centered at 4. Okay, and we know that was centered at 4 because we've been saying that. And we know by the graph, just to kind of look at that, that's around 4. This is a behavior. So what happens is, you do have these technology calculator devices that will use this information to approximate around the value 4, Anyway, let me see if I can give you a little bit of more detail. Well, whatever. We're going to move on. So let me demonstrate to you guys another thing that's really important to know, where some of these other expansions may come from. Right? We've seen e to the x yesterday. And now, very, very common, they want the Maclaurin series for sine. Okay, so you say, oh, they're going to have me do this. I need the coefficients. Yes. So essentially, you focus on the coefficients. And that's really focusing on the derivatives, evaluated at 0. And I should say, if I focus on the coefficient, you're really focusing on this. Okay. So you might start by saying, well, what is this? Well, if the function is sine, what's the derivative of sine? Cosine. What's the second derivative now? Well, it's a derivative of cosine. It's going to be what? Minus sine. What's the third derivative now? Derivative of minus sine. What's the derivative of minus sine? Is that minus cosine? And then the fourth derivative. Let's do 4. You're back to sine. What you really need is to put what here? We need the zeros because it's Maclaurin series are centered around the origin. And so I need those coefficients here. Okay, so you say, well, what is that going to be? Well, sine of 0. Do you guys know what f of 0 will be? What's sine of 0? Is that 0? I think so. What's cosine of 0? That first derivative. Isn't that going to be what? 1? F double prime is 0. F triple prime is negative 1. And then the fourth derivative, evaluated at 0, will be 0. And the reason I stop here, why did we stop here? Do you guys know? Because this pattern that you guys see here is going to repeat forever. That sequence is 0, 1, 0, negative 1, 0. You guys know what a sequence is. 0. You're going to see that sequence repeat forever. 0, 1, 0, -1, 0, 1, 0, -1, 0. That sequence goes on forever for that derivative evaluated at 0. So what that really means for us, we've found this is the important detail. That's the numerator. The denominator is going to be n factorial. So you say, is the denominator going to be n factorial? Yes. And then, of course, we have the variable here, x to the n. So altogether, you might say, well, what does that look like then? Well, it looks like what we can say is sine, starting off, 0 plus 1 over 1 factorial. Yes, that's 0 factorial. Okay. X plus, now 1, I'm sorry, not 1. That pattern's going to continue, 0. I'm looking at this pattern here. Two factorial, x squared, -1, 3 factorial, x cubed. Okay, so we're looking at that 0, 1, 0, -1, x cubed, and then we know the pattern what? Continues again. So that'll be 0 over 4 factorial, x to the 4th, plus 1 over 5 factorial, x to the 5th, 0 over 6 factorial, x to the 6th, -1 over 7 factorial, x to the 7th, because those numerators are doing what? That's the pattern. That's the sequence. Simplifying this, 1 over 1 factorial x minus 1 over 3 factorial x cubed, 1 over 5 factorial x to the 5th, minus 1 over 7 factorial x to the 7th, plus this pattern goes on forever. And what people want to always remember or know is what's the relation, how do you describe these terms? Do you guys know what's unique about that? Because this is the first power 2. What's unique about those numbers? 1, 3, 5, and 7. They're odd, is that right? So I want you guys to note something here. For the odd, how do you represent odd numbers here? Well, there's 2 ways. You could say 2n plus 1 or 2n minus 1. Sometimes they go to k, 2k plus 1, 2k minus 1. Okay, so this is how you generally represent odd numbers. But what also is happening, don't forget this, is you start with a positive, negative, positive, negative. What also is happening? You have alternating. You have the alternating mechanism. Is that right? So I want you guys to know, how do you represent alternating? Well, that's -1 to n, or -1 to the n minus 1. It depends how you start, and it depends on what you let n be. So if we're going to write sine where this summation starts with 0 now, that first term, you're going to have to use -1 to the n, because, and you could use -1 to the n plus 1, by the way. This is what the different ways we can do the alternating mechanism. I know we've been doing that in purple. So since it starts with a positive 1 and we start with the index of 0, I'm going to leave it as it is. But then now you say, well, how do I get the odd? So you go, okay, that's 1 over, or really they put that, since it's 1, they put that over 2m plus 1. Don't forget to put x to the 2m plus 1 as well. And I guess I have to erase this here. Yeah, factorial. I apologize. Don't forget to put the factorial there. Good. Okay, good job. So this is how they get the power series expansion for a sine, by the way. And then you say, well, how do they know this is for all x? Well, you could use the what? The ratio test. So this is good for all real numbers. So I want you guys to also note, now remember, this is the Maclaurin series expansion. This is around what? Around 0. The center is at 0, Maclaurin series. So, all right. So I want you guys to understand this too, because this is kind of fascinating. Sine, if we looked at those first terms, is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. If we only looked at the first 3 terms. Okay, you guys okay with that? Right? So you guys know where I'm headed with this. To keep this interesting, y is sine. Don't forget this is expansion around 0. There's my sine curve, and here's where 0 is. So y is going to be what? X minus 1 divided by, do you guys happen to know what 3 factorial is? That's 6. I'm not going to take the chance that this knows what factorial is. It probably does, but okay. And now this is going to be plus, well, what's 5 factorial? Do you guys know what 5 factorial is? I think that's 120. Now this will be x to the what? 5th power. Ooh. Let's see if we can understand what we're looking at, ladies and gentlemen. And again, this is around what number? 0. Wasn't that power series expansion around 0? So, I mean, chew on that a little bit. Man, what is that? Look at that. The green curve is sine, and this polynomial really pretty much approximates it around 0, very close to 0. Okay, so this is a power series expansion, so we can approximate this curve around 0. Anyway, so you might say, what about cosine? Well, cosine, ladies and gentlemen, very, very, very similar to sine, but you might say, how do I get that? Well, you know what they do? They differentiate what? Sine. But they use the power series expansion formula. Sorry, I'm running out of space. I hate when I do that. Okay. All right, and I'm probably not going to be able to move anything. Oh, there we go. And again, the derivative of a sum is sum of derivatives. And then we can simply pull out our constants here. Okay, and then I get to differentiate a nice polynomial. Let's see if I can remember how to differentiate. Isn't that 2n plus 1, x to the 2n plus 1 minus 1? Is that true? Is that right? You guys with me on that? And then, do you guys know anything what's going on here? What happens here? Do you guys remember? How do you write 2n plus 1 factorial? Isn't that 2n plus 1? Now, what's 1 less? 2n factorial? So your 2n's go away. So what I'm saying is cosine is described in terms of a power series. X to the 2n, I guess we put it over here, over 2n factorial. And it has the same, okay, this is the Maclaurin series. This is around the center, a is 0. Because I differentiated a Maclaurin series, and it preserves the what? It preserves your, what we call this interval of convergence. Okay. So, ladies and gentlemen, going back over up here, or going to the very popular, if you said, whoa, they got sine, cosine. Really, they don't do tangent. This is going beyond the scope of the course. Calculus 2 doesn't have tangent or secant or inverse sine, inverse cosine. You have inverse tangent. But, you know, if you look in your book, they're going to limit to that. Your book is going to have 1 over 1 minus x, e to the x. Your book has sine, has cosine, has inverse tangent, ladies and gentlemen. So look at the power series for your book. I gave you more here. We're not going to use these others, but I copied it from a website, but I actually put the reference links there. I believe I did. There you go. Yeah, I put the link there. So I just gave you more than you actually, let's go back, than you actually need. All right? So gave you guys more. And so this is all the power series expansion. So just to kind of give you guys another quick example of a power series expansion of how to use some of these here. Okay? Maybe I have to go back and look at, do I have to look at my study guide? Where is it? Let me look at my study guide. Oh, here we go. We can try to do something like this. Yeah, let's look at an example of something like this so you guys can see. What if they give you the function here? I'll just change it to sine, maybe 4x. Or okay, we can do x over 4. I don't think we've done a fraction. Is that right? And they want the Maclaurin series. So technically, they can say, what's the Maclaurin series expansion? Right? So you're going to go back to the original, right in here. Put a triangle here. Put a triangle. And I think we've been using the color green. Is that right? Do you guys know what I'm saying? Just plug in green. What do you guys plug in? Yeah, so is that right? I mean, I think is that okay? What do you guys think? What are you really going to do? It's over here. You use your algebra. Is that right? It looks like I'm okay. Is that right? So here's the power series expansion. Again, this is good for all real numbers. Convergence, any value of x. But it is centered around 0, so you guys know. A equals 0, that's your center. Because it's a Maclaurin series. Right? We derived this as a Maclaurin series originally. Centered around 0. You might say, why do I put that center around 0? Because if you go back and if you said, can I approximate my curves? Yes, but around 0. It'll converge for all x, but it's going to approximate around 0. What if you said, I want to approximate this so you guys know, let's approximate this around pi or something. If you change the center, well, then this is now going to be what? What do you have to use? The Taylor what? Series expansion. It'll look different. Okay, just want to throw that out there. Yeah. No, if the center is pi. Yeah, so remember A is a center, right? So if you said to me, why do I change the center anyway? Or why would a Taylor series expansion exist for these kind of things? Yeah, because if you want to approximate sine like you're doing here around 0, good, you use a Maclaurin series expansion. So you're approximating sine around 0. But what if you said, no, I want to approximate sine around what? Over here, around pi. I don't want to approximate around 0. Around pi, which is over around here. There's pi, by the way. It would be a horrible approximation. You say, why would it be a horrible approximation around pi? Because it's not even close. There's a difference there. See if I can do that. Can I find it? Yeah. No. I guess it doesn't want me to do that. Okay. So what I'm saying is around pi, that same power series expansion is no good. Can't use it. You go, what do I do then? Well, you go to Taylor. You go, what in the world is Taylor? It's right here. You still do the same process, but now it's going to be around pi. So you go, I need Fn of pi now. You go, oh, how do we do that? Well, go back now and see if I can copy this here or erase. You go, well, what happens if you said, no, not Maclaurin? We want what? The Taylor series expansion, because your center is no longer what? 0. Okay. My center is now going to be what? Pi. So replace, you have to put pi. So you're going to have to know, what is sine of pi? Do you guys know what sine of pi is? Right? Yeah. Let me see if I can do that here. F now of pi. So all these are going to be pi. So you want to see what kind of sequence you get. Right? What's the sequence now if we change this to pi? And you go, oh my God, you're using the language of sequence. Yeah, we know about sequences. So sine of pi now, that's 0, is that true? What's cosine of pi? -1. And this will be 0, and this will be +1, and this will be 0. So the point I want to make is that sequence now is there. It's very similar, but it's 0, -1, 0, 1, and 0. Is that right? It's a similar sequence. So I kind of write that down. You go, oh, okay. 0, -1, 0, +1, and then 0, it's going to repeat. 0, -1, 0, 1, 0, -1, 0, 1. The pattern goes on forever now. So let's just see how this changes. So now it's 0, what? -1. Okay, plus 0, plus 1. See if I can put, let me do that. The details. 0, -1, 0, 1. Then 0 again. -1. And then 0. And this is +1. Alrighty, so let me see. Yeah. So now we're going to start with what? -1, 0. And this is +1, 0. -1, 0. +1. But be careful here. It's not x anymore. It's not x squared. These terms are changing. Be careful. Let me see if I can move and expand. What do I mean? Do you guys know what we're talking about? What else do we have to change? This is now what? That's x minus pi now. So if a in this example is pi, this is centered around pi. So it's not x anymore. All right. So let me see if I can get the sequence here. Let me just change it. So we can try to change that here. So here's what you'll have. -1, 1 factorial, x minus pi to the first power, plus 1, 3 factorial, x minus pi cubed, minus 1 over 5 factorial, x minus pi to the fifth, plus 1 over 7 factorial, x minus pi to the seventh, right? And that goes on forever. So the Taylor series expansion, I didn't want to erase that, but we can. Now you say, what happens if I start with a negative? Right? This is going to be over n factorial now, x minus pi. What happens if we start with a negative and this is 0 like we've been doing? Oh, we have to do 2n plus. Let me apologize here. We have to do what? 2n plus 1 factorial. This is also 2n plus 1. But we start with a negative, and that's 0, so I can put plus 1. So I change the power to put plus 1, and now you have the Taylor series expansion for sine, where, what's the deal? This is around pi. Your center is pi now. Okay, so let's see what sine looks like now around pi here, right? Look at the first few terms. So if n is 0, that's negative. I think we have it up here. We got negative x minus pi. So it starts with a negative, and then it's going to be plus 1 over 3 factorial x minus pi cubed minus 1 over 5 factorial x minus pi to the 5th power. Okay, I'm going to try, 3 factorial here. Okay, so now let me see if I can do that here in Desmos. I'm gonna compare y equals negative parentheses x minus pi, come out, plus 1. What was it? You guys remember? I think it's 1/6. Yeah. 1 divided by 6. Raise that to the 3rd power, I believe. Okay, come out of there. Minus 1 divided by, I believe it's 120 again. But now it's going to be x. So x minus, and let's get rid of purple. There we go. Okay, so pi's are out over here. Do you guys remember? So let me do this here if you guys can see that. Do you want to change the color? Is it too hard to see? Okay. What's my point? The green is a sine curve. Is that true? So, no, let me go back. Yeah, the green is a sine curve. The red is the approximation, but it's now a Taylor series. And so if you change that idea of the center, you're changing, this is now, A is not 0. Everything doesn't center around 0. So if you wanted to approximate the sine curve around pi, what you'd have to end up doing is using the Taylor series expansion. This is why it exists. And now you guys can see why you need both. Because approximating that curve then, what's the story? You're changing the location of the center. You're changing where you approximate. So we can approximate the sine curve with this polynomial. It's a 5th degree, by the way, polynomial. And that's why you have Taylor series. Change the location of the center, ladies and gentlemen, and you're going to change what? You change everything. It's a different polynomial approximation. So anyway, I can do this stuff all day. I love it. What do you guys think? You guys see my point? And let me ask you a question too. My personal feeling is graphing this stuff in Desmos the way we've been doing it is been an invaluable tool to describe power series expansions and Maclaurin series and Taylor series. Because without it, I think people have a harder time seeing why you do it. And moreover, you know, and this is what we're saying. This is the Taylor series expansion. It's a different polynomial. Oh, and I think I screwed up. Oh, no, I didn't. I'm fine. I didn't screw up. Sorry. I think I want to just write a nicer 5 factorial. Oh, good. Right here. It's okay. The question's really regarding the alternating mechanism, right? So remember, this starts with a negative. If you put -1 to the n and n is 0, right? If you put -1 to the n, but you let n be 0, right? Isn't that a positive one? So you'd start with a positive one. Remember, this is your n value. So how you start with a -1, there's really two ways, is you change this to be +1, or you could do n minus 1. I choose +1. I keep it simpler in that way. So how you change it is by adding 1 to that power. And now you're going to start with a negative when n is 0. And that's why the change was right in here. So this is the essence of the question. Whatever happened to that power? Why did you do that? Well, because that's how we started the series. And as you guys can see, yeah, it starts with a negative, positive, negative. It's alternating. And then in Desmos, we did write it correctly. So you can see very beautifully that approximation now. And anyway. So let me double check something really quick. For you guys, let me double check. Oh, what am I doing? Am I checking? I have to remember what I'm checking. I get so involved with this stuff. Yeah, so if you look at so what you guys look at your book, you'll find like, hey, they don't give me all those expansions like Mr. Judge has on that sheet. I go, I know. They do give you some. Let's see what we can do. Hmm. Well, I think we should do. Yeah, I don't know. So, I mean, there's a few you can do there. I don't think. Not much, but we should say, yeah, we said odds. So you can do a few of those odds. Anyway, okay. So, okay, ladies and gentlemen, there it is. There's your Taylor series expansion and an example of that. Maybe you want to do a couple on your own and see how that goes, you know? I don't know. Let me change that.